I learned a tough lesson this morning. It is really hard to put on a mask when you're already wearing over-the-ear earphones. But I made it stick, so I feel good about that. All right, these are off-ish. Now they're off. You still don't have the quiz. I'm combining the week 2, week 3 quiz. It's going to be due Friday this week. It'll be posted noonish today. So look at it before tomorrow. And if you have questions, be prepared to ask those questions tomorrow during class. Tomorrow during class, we're going to, tomorrow during class, we talk about manufacturing economics specifically, but that segues very well into the group project that we started talking about already in the term. And so we'll explain the assignment of the group project and the details of that tomorrow in class. And also tomorrow in class, we'll talk about the CAM project. So the thing that you get to do to demonstrate your ability to use the CAM software. All right. So I think I told you guys a story about a purchase order that I had, and it was a $200,000 purchase order. The first $25,000 was to figure out how to make the part. I told that story already? Yeah. And we got, 2 weeks into making that very first part, the $25,000 part, 2 weeks into it, when the customer realized that they had sent me the wrong drawing. So as a manufacturer at that moment, as the, I like to refer to this person as the cranky old machinist. And that's partly because I experienced some cranky old machinists when I was a young engineer. So as the cranky old machinist in this story, what's the first thing that goes through my mind? When I realize that they've given me the wrong drawing, they've contracted $25,000 to make the wrong part. What's the first impulse I have? You guys can guess. Deliver the part, right? We clearly had a contract. Legally, I was obligated to give them the part that they had asked me to make, which was the incorrect drawing. Now, was that going to engender goodwill for my business? No. So, of course, I didn't do that. But this is something that I learned as a young engineer doing design work, and my young engineer time, I don't know, I probably spent 6-7 years as a young engineer, intermittently doing design work, sending work out to machine shops and things like that to get parts made. Have you guys all heard of engineering judgment? Somebody tell me, what does engineering judgment mean? Somebody in the back, tell me, what does engineering judgment mean? Red WPI sweatshirt. You've heard of it, right? You've never heard the word engineering judgment. Really? Who's heard the word engineering judgment? You're lying. You lie about other things too. Okay. So engineering judgment is when the engineer doesn't want to do all the design work. Because they know intuitively. They use their judgment to know that the thing they've decided to do is going to work. Right? So who's ever been outside during a rainstorm? Who's ever been outside during a rainstorm on purpose? Right? And what was your purpose? Was it to dam up the little stream of water that was going and like make a lake and divert the water down different ditches? Who's ever done that as a kid? Right? A lot of us have done that, played with making the water flow, right? So when you put the pile of dirt or the big rock in front of the stream of water, did you design the dam? You were clearly doing civil engineering at the time. There's no argument of whether or not you're putting this pile of dirt in front of the stream of water coming down the driveway was civil engineering. That was civil engineering, 100%. But did you design it? No. You used your engineering judgment. And you decided that by putting this big thing in the flow of the water would divert. Right? So you all have exercised engineering judgment. You could think of some time, if it wasn't playing with water or mud in the yard. Sorry. I have to think for a second here. I have a daughter. She doesn't do it anymore. But she used to manufacture. She loved mud. I mean, she would manufacture mud. If there was no water available, she would put some dirt in her mouth and spit the mud back out. She loved mud. And so I think about that. So we're certain that she could identify, she's probably going to be a geologist. She could identify all rocks by taste. She probably wouldn't be happy if I was telling that story out loud anymore. All right, so engineering judgment is when we know in our mind that this solution will work, so we don't bother to do the math. And so we've all done that, right? You've answered homework questions that way. So when I was a young engineer, I liked to practice my engineering judgment. Why? Yeah. I didn't have to do math, right? Right. I mean, granted, we become engineers because we're good at math, but skipping the math step makes us feel so good sometimes. So I like to exercise my engineering judgment, and I would change a design to have fewer fasteners. Now, why would I want fewer fasteners? Yes. So reduce cost and weight, but that wasn't the real reason. Yeah, and that was me. At that particular job, I reduced the number of fasteners because I knew I had to assemble the thing once all the parts came back. And I didn't want to screw in all those screws. So I took out every other one. Right? My boss was pissed about that. Because I used engineering judgment. And when you're a young engineer, you don't really have engineering judgment. Engineering judgment comes from experience. Right? So you get the ability to know that it's going to work by having made mistakes and seen stuff not work before. So I use my engineering judgment. The other place that I really like to use my engineering judgment, and I'm not certain this one was my fault, was, although, can I really blame the professor teaching the class? If the professor didn't teach me well enough, is it my fault if I didn't learn? All right, this is an existential question. Whose fault is it if you don't learn the stuff you want to learn in this class? Stand up if you think it's my fault if you don't learn the stuff you want to learn in this class. All right, so is everybody learning the stuff they want to learn in this class? Or are you just good with not learning it? Because that could be the answer too. All right, so I didn't learn very well how to do geometric dimensioning and tolerancing. Nobody at WPI taught me very well how to do geometric dimensioning and tolerancing. In fact, I'm not sure anybody at WPI taught me the phrase geometric dimensioning and tolerancing, which we shorten up to GD&T. So I didn't know anything about the standards for creating an accurate drawing or a drawing that truly represented what I meant to the manufacturer, using all of the correct symbols, using all of the correct, so who's had ES 1310? Right, so they talk about GD&T in 1310, right? So you get, I took ES 1310 also. And I'm certain that the professor said the words, at least like geometric dimensioning and tolerancing. I'm certain that she said those words. I didn't learn it. And I didn't understand the importance of it. So what is GD&T? Somebody who's taken 1310. Explain to me in 1 or 2 sentences, what is GD&T? Yeah. So, yeah, there you said a keyword there. Standardized. All right, keep going. The standardized way to Okay, so he says a standardized way on an engineering drawing to show how much we can screw up. All right, so that's the tolerancing part, right? It's how you represent, organize, and represent. So it's how you organize and represent the information that you put on the engineering drawing. So the tolerancing part allows you to tell the manufacturer how much they're allowed to screw up when they make the part, right? It allows them to know what's the variance that is still acceptable to the customer. So that's really important for 2 reasons. It is impossible to make the part perfect. Any part, it is impossible to make the part perfect. And even if you do the impossible and you make the perfect part, it is impossible to know that you have, because you have uncertainty in incoming materials. The materials change. There's random vibrations. There's random people walking in front of you. All kinds of random things that happen while you're making the part that make it vary just a little bit. But also you have an extreme uncertainty in your ability to measure the dimensions of the tolerance parts of your drawing. So it's impossible to make a perfect part. Tolerances are required to enable us to make parts. Who's ever made a drawing and not put a tolerance on the drawing? I'll raise my hand. I do it all the time. I prefer to call it a sketch when I know that I haven't followed GD&T. If I call it a sketch, then I didn't have to follow GD&T. It's just a sketch. It's a representation, but it's not a drawing. In order to really call it a drawing, it has to follow the GD&T rules as defined by ISO or ASME. So ASME B14 Y14, ASME Y14 does the standard for representing drawings. There's an ISO committee that does that too. I don't remember the name of the ISO committee. I do remember that it is TC H31 that represents ASME at the ISO meetings. Little trivia for you. So what are these? So it's standardized. It's a standard. What's the purpose of the standard? What's the purpose of a standard? Yes.
Make sure everybody does something the same way.
So he says to make sure everybody does something the same way. So I sit on a standards committee, and I've been active in some other standards committee groups. So the purpose of a standard, well, is to sell books, right? ASME and ISO are publishers. ANSI and ISO are publishers. We write standards for them so that they can sell books. So at one level, if you're the publisher, purpose of a standard is to sell books. Is that really the purpose of a standard? No. The purpose of the standard is to facilitate communication. And it gives you a specific way that you talk to your vendors, and vendors talk to their customers. And that way, we all know that we're all speaking the same language. And so this GD&T specifically tells you what the format of the drawing should be, how to represent things. What are some rules when we do a correct drawing? What are some of the most important rules that you learned? So two-dimension lines shouldn't cross over each other. Why don't you want two-dimension lines to cross over each other? It's confusing to the person who's reading the drawing. Where does the cross, what does the cross mean? Which one is dimensioning which? If they never cross each other, you can't have that confusion. What's another thing that you don't want to do in a drawing? One that I remember is you can't over-constrain. In your solid modeling programs today will tell you this. When I was doing this, they taught us how to roll the pencil so that the line width would always be the same as you drew across the paper. So when I took ES 1310, 50% of the class was with a pencil. The other 50% was with a computer that didn't work very reliably. And so what I learned, one of the things that I took out of it, the only thing I really learned was you can't over-constrain something. So if I say, make this one go up, right screen up. So let's say there's a hole here, right? All right, so I've got a hole, and I say this is 2.5 inches. I say this is 2.5 inches. How long is the part? Part's 5 inches. So can I do this? Is that still correct? What? Why is that incorrect?
Because the 2.5 shows where the center of the hole is. So if you just put 5, the hole could go anywhere.
Well, no, because it's an addition. It's an addition of the two 2.5s. So you're thinking I could leave that part out is what I meant? I didn't mean to leave that out. I mean to include both. So, yes.
If you include both, then it's kind of like saying that has to be. If you say like 5 there, then there can be a tolerance on the 5. If there's one 2.5, there can be a tolerance on the 2.5. But if there's like two 2.5s, then like there's an addition of uncertainty that like over dimension.
So it's over dimensioned, over constrained. The reason is exactly what she was saying. So if so there will be a tolerance, right? Physics says that it is impossible to make a perfect part. So it is impossible to make this part. And even if you did make it, it's impossible to know that you did make it. So everything, whether you've specified the tolerance or not, has some implied tolerance. And so in our drawing block, we typically have down near the bottom there, there'll be things such as tolerances. And you'll say something like 0x is plus or minus, I don't know. And 0x is plus or minus 0.005, something like that. And you can go down to x is maybe plus or minus. So if it's 3 decimal places that you've specified, it needs to be plus or minus half of the next decimal place. So this is a pretty common standard tolerance block. In fact, I bet whenever you pull up a template to create a drawing in your CAD software, CAD software, I bet whenever you pull that up, you'll see a tolerance block come in, and it may or may not have information in it. If it does have information in it, it probably has whatever you said last time you used that software, right? And it's just it's a placeholder, right? So if here I specify plus or minus something, so say plus or minus. So I put that there. It supersedes whatever's in this tolerance block. So if you call it out specifically on the drawing, it supersedes whatever's in the tolerance box. But even if you don't, so if you don't fill that information in, if you don't give any kind of tolerance information on your drawing, the first thing the manufacturer, or the cranky old machinist, as I like to call them, the first thing the cranky old machinist knows is that you don't know nothing, because you haven't given them a drawing. Maybe, now if you told them, I have a sketch of this thing, and this is sort of what I want it to look like, that's different. If you say, here's my drawing, make this part, you haven't given them a drawing if you haven't filled in the tolerances. If you've over-dimensioned it like this, so this 5 number has to have a tolerance too, right? Right, so let's say it's plus or minus 0.1. So if this could be plus or minus 0.1, and these could be plus or minus 0.01 each, which tolerance is correct? But does the manufacturer, does the cranky old machinist want to know how long the part is? So maybe what's important to you is that this hole is in the center relative to the 2 edges, right? And if you don't put this dimension on here, that's what you're indicating to the manufacturer. You want this hole to be in the center relative to the 2 edges. And the part could be plus or minus what? What could the length of the part be? Plus or minus, yeah, 0.02. I had to count the decimal place there in my head, right? So it could vary that much. If you put this 5 here with any tolerance, even if you put the 0.2 tolerance, you've made it hard to make the part. Now, the machinist, though, wants to know how big the part is, right? Do they want to have to add 2.5 and 2.5 to get 5? Do they really want to do that? No. They want to get the print and say, oh, it's 5 inches long. So to do that, you can put that 5 in parentheses. That says it's for reference only. So I've given you this extra information just for your reference, but these are the tolerances. So that's one way that you can indicate to the machinist, the cranky old machinist, you can indicate to them, yes, I know how to make a drawing, but yes, I know you'd rather know how long the part is, even though that's not as important to me as the thing being in the center of the part. Okay, so those are some of the things, and we're gonna talk specifically about GD&T. I think next week. I don't remember the schedule off the top of my head, but being able to talk to the machinist as if you know something will make you a better engineer. And the reason for this. So who's ever heard of Once Upon a Time? So who's heard of the skills gap in manufacturing? Really? You guys are all here at WPI, sitting in this class. Nobody's ever heard the term skills gap in manufacturing. You've heard the term skills gap? Anybody else? Just heard the term. Maybe on the news. You've heard it. So within 10 years, so what drives any economy? Currently today, what drives any economy? She says money, you say demand. What makes all the stuff that's in demand? Manufacturing, right? So manufacturing creates all the stuff like, oh, here. I haven't really been paying attention. Manufacturing creates all the stuff that the demand is for, that the people pay the money for, right? Maybe not all the stuff. Okay, manufacturing didn't create the Netflix special that I watched. It's Netflix series that I binge watched over the weekend. Right? Manufacturing didn't create it. It did create all the cameras they used. It created all the props they used. It created all the clothes they were wearing. Right? So manufacturing creates the stuff around us. So if there's a skills gap, so what does the term skills gap mean to you? Somebody tell me what the term skills gap means to them. Yep.
There's a group of people, and some of them have more skill than others, but the important part is that there's a large gap in the middle of
Okay.
skills.
All right. So there's people that have skills, people that know how to do stuff. There's people that don't know how to do stuff. All right. So that defines a skills gap, right? What are the stuff people know how to do that would be important to manufacturing? What are the kind of skills that would be important in manufacturing? To operate a manufacturing company, what are the skills people need to have when you hire them? So CNC machine. So we want a machinist. Back to my can't spell. We need machinists to run a CNC machine shop, you would think, right? What's a machinist do? Yes. They work the machines, okay. So you mean like put the part in, press the start button, take the part out?
Make sure that they don't do anything stupid that gets the machine broken when they do it. Yesterday, who was in lab yesterday? Who heard the horrible noises coming from the milling machines yesterday? Yeah, me too, because I was the one with my hand on the red button after the first time it happened. And so one of the things I was doing was trying to not break the machine. Broke 3 end mills. Didn't break the machine. And I think I've solved the problem. But I don't know, because James is trying it out right now while we're here talking. So they work that machine. So what they have to do is they have to figure out how to take your drawing. They figure out how to fixture the part in the machine. So how to hold the part in the machine, which was the problem yesterday. I could not fixture the part well. So the part kept moving every time the tool was touching it. So fixture the part of the machine. They figure out the tool path. How to move the tool through the workpiece material to make the part. They figure out how to measure. They figure out how to make sure that they've hit the tolerances that the customer asked for. They know how to fix parts when they don't meet the tolerance. They know how to put them back in. They know how to hold. All right, so they do all of the stuff that allows the part to go from here to you. All of the stuff. Now, some of it could be done by a programmer. Some of it could be done by a setup technician. Right? Some of it could be done by the QA guy, right? QA tech. And so companies are trying to hire people that know how to do a little bit of setup. They're trying to hire people that know how to do programming. They're trying to hire Q&A people that can measure something and tell you whether or not it works. The machinist does all of this,
and does it faster and better than anybody the companies can hire. Why is that possible? It's what they do. So you guys have heard that 10,000 hours will make you an expert at something? 10,000 hours of practice. So what these people get coming in isn't 10,000. It's a great TED Talk. What's the guy's name? He wrote the Personal MBA. Josh Kaufman. Great TED Talk by a guy named Josh Kaufman. He will dispute the 10,000 hour requirement. So what's the guy's name that said 10,000 hours? He also has a TED Talk. I can't remember the 10,000 hour thing, but everybody believes 10,000 hours. It takes 10,000 hours of practice to become an expert at something. So with 20 hours of practice, you can become good enough to do something. That's what Josh Kaufman says. And so with 20 hours of practice, you can become a setup technician, you can become a programmer, you can become a QA tech. These guys don't have 10,000 hours of practice. They have 100,000 hours of practice. They do it in their sleep, right? They can intuitively know the answer. They have engineering judgment. So within the next 10 years, we will be missing 2 to 3 million of those people in the US economy. Within the next 10 years, they predict that we'll be short $2 to $3 million of skilled people in the manufacturing workforce. What's that say for our economy? Nothing good, right? Right? Companies that survive are going to have to figure out how to design stuff and make stuff so that these people with 20 hours of experience can still get it done, right? Yep. You guys know, you realize this because those people are retiring. Because these people with 100,000 hours of experience are 70 years old.
I mean, I'm maybe just a misunderstanding what the skill gap means. It's just if someone has a lot of experience, that means they've been there for a while, so they're going to be old. Wouldn't it be relatively common for people with that kind of experience to retire?
So the problem, the cause of this skills gap. So that's a good question. So isn't it normal for people to get old and retire? Right? We kind of expect that in our society, right? We get to a certain age, we retire, we go play golf, sit on our boat, whatever it is we like to do when we're retired. So the problem is for 40 years, we haven't been making new machinists. There was nobody coming into that role, or at least the volume of people coming into that role was so small, it's not having enough impact. And the reason is because people thought manufacturing jobs were dirty. People thought manufacturing jobs were loud. People thought manufacturing jobs were boring. So when the recruiter would come out and say, hey, who wants to come work at a manufacturing facility? Nobody wanted to do it. And our parents, whose parent said, go out and get a union job in a manufacturing company? Anybody here? Do your parents tell you not to go to WPI and instead get a union job at GM? Right? But 50 years ago, your parents did? No, there's still union workers at GM in the US. You totally get a non-union job at Toyota in the US. So, how much money do you think these guys make? Well, if they're not a machinist probably until 10, 15,000 hours. They may have that job title. They may think that they're a machinist. A lot of people think they're a machinist as soon as they've run a CNC machine once. So to get somebody that is actually an expert, you can't hire them around here for less than $100,000 a year, which doesn't sound like a lot to you guys, but it's a lot compared to $15 an hour. And so these people, so this is the button pusher, right? So button pusher is making, I don't know, 15. Setup, programmer, QA, these people are probably making 20 to 25 an hour. And these guys could be making 50 to 60 an hour. So there's difference in skill there. So that's hourly rates, right? And you guys will make somewhere between them and them when you graduate, probably, as engineers. But your job as engineers is going to have to be to replace them and make them unnecessary, because there simply are not enough people coming into the workforce right now that are intending to get these skills and that are acquiring these skills at a fast enough rate to replace the 2 to 3 million people that are going to be missing 10 years from now. So why do I say today we want to talk like a machinist? Go ahead. So I want to challenge all of you to learn as much as you can from these people before they're gone. Because there are skills that they know how to do that are disappearing, and nobody in the world will be able to do that again. Because ever watched like Ancient Aliens? Raise your hand if you know what I'm talking about when I say Ancient Aliens. Ever watch any of these UFO shows where they talk about all the UFOs that are coming and have been coming for years and years? If you don't watch the shows, you know what I'm talking about, right? So there is a school of thought that says none of these people are aliens, but that they're ancient people from the earth. And that there were civilizations that grew and collapsed 50 million years ago that we don't know about because there's nothing left of their civilization. So just think for a minute that might be true. So that the pyramids were 50 million years old, not 5,000 years old, right? And think for a minute that might be true, and imagine how a society that gets so advanced collapses. You get dependent on, so how does our society grow right now? We're growing our society right now by inventing new technologies, right? It's one of the most exciting times to ever have been alive right now, because of the rate of change of technology, the rate of change of society around us. This is cool. But we're also forgetting old technologies. So we couldn't build Wilkinson's boring machine today. Not with the same technologies that he used to build it. It was Wilkinson's boring machine that enabled Watt to make steam engines that enabled the Industrial Revolution. We don't have this, even these guys don't necessarily have the skills to build that machine again today. So we want to go to Mars, right? Apparently a lot of people want to go to Mars. Some people just want to go fly around for 4 days. Apparently a lot of people want to go to Mars. And they say the first step of going to Mars is to go to the moon, right? Well, didn't we go to the moon 50 years ago? Why don't we just hop in our rocket ship and go to the moon? Anybody know why we don't just hop on our rocket ship and go to the moon today?
I mean,
We still have all the drawings for the rockets to send us to the moon. We have all of the GD&T.
because the rockets used back during the Cold War period were extremely expensive and not exact. There's just not. It's cheaper and more efficient to send a probe.
Okay, so it's certainly cheaper and more. I'm not certain. I understand the argument to say it's more efficient. I'm not certain it is more efficient to just send a probe, because it's hard. We don't have enough AI yet on the probes. We have a professor working at WPI right now who worked on the Apollo missions. So they're not all dead yet. In fact, anybody see Apollo 13? So do you remember at the end of the movie where he's guiding the thing back in and he's got to focus on the corner of the cockpit window to guide himself in because none of the instruments worked? So the professor at WPI is Jerry Schofield. He teaches in the School of Business. He was working on the guidance system for that module, and it was hydraulically actuated. It's pretty cool. And he said, when they said, you got to turn the power off and you let everything cool down in order to solve their problem, he said, you will never restart the guidance system. And they're like, well, what are we going to do? And he's like, they're going to have to use the corner of the cockpit window to steer. They're going to have that reference. And so when he was at the movie theater watching the movie with his wife, he's like, I told them they had to do that. That's pretty cool. So it's not that those people aren't around anymore. Go ahead. Well, nobody's made those parts in a long time. But you would think if we have all the drawings, we could make the parts again. We've lost some of those skills. So we're reinventing those skills now. Now, yeah, sure. We're also 3D printing nozzles for our rocket motors to make them a better shape, because there's shapes that you can 3D print that you can't CNC machine. In fact, they made a lot of those rocket parts without CNC machining. Most of those rocket parts were made on manual machine tools, etch-a-sketch style, like I like to call it, by really skilled machinists. A couple years ago, I went to look at a machine shop that was for sale, and they made little rotary couplings. They had a product line. They had parts that they had made here in Massachusetts that were still sitting on the moon as part of the moon rovers. So that stuff still exists, but we don't have it all together. We don't have all those skills. So now we're reinventing all those skills because we put it together as a crash project. And I think they're trying to save money. You're right. We spared no expense when we were going to the moon because we had to beat the Russians. Right? Now all we have to do is beat Virgin Galactic. All right. So I want you to learn. So all right. So we talked about, we want you to have good GDT in your drawings when you go talk to the machinist. I did a presentation. A couple years ago that I want to end today just by going through this. And it's the 5 things you need to know before talking to the cranky old machinist. Come on. So I created this presentation for WPI graduate students to learn what they needed to consider before they asked for help on their projects, certainly before they sent their drawings out to the cranky old machinist at a job shop to make it for them. So I said, it's easy. There's only 5 things. 1, it will take longer than you think. You need to know what it is you're making. This is especially important for graduate students and undergrads here at WPI. You need to know why you want to make it that way. And you need to know what you're going to make it out of. So when you're talking to that cranky old machinist and they ask you a question, 1, don't ask them, can you make it today? I mean, something's actually got to be on fire before you ask them, can you make this nozzle so we can put it on the end of the hose so we can put the fire out? Okay, that's fair. However, if they like you, they might make it today because they want to teach you something and show you the better way to make it. So you need to know why you're making it that way, what you want to make out of and why you want to make it out of that. And you need to know that the design part of the process is your job as design engineers, not the machinist job. All right, so it's going to take longer than you think. So if you send out a part for a quote, 2 to 3 weeks is probably a reasonable lead time for getting your part back. Now, we talked about this at the beginning of the term. When the customer sends the drawing to the machine shop to get a quote, what do they want? They don't want a quote, they want their part, right? But they've got to understand that it's going to take longer if their design sucks. So the quality of your design matters. The number of parts in the queue ahead of you, right? So this, you can't have it today because they're making somebody else's part today. It's also going to depend on the number of parts you need, obviously. That makes sense, right? Intuitively, we all knew that. If I need 100,000 parts, it's going to take longer than if I need 1,000 parts, than if I need 10 parts, than if I need one part. So if you only need one part, you may never get it. So whether or not the machine shop has the stock material on hand, are you using some exotic stock material that they have to order? Or using something that they normally use? And you need to remember that the quality of your design greatly impacts how long it takes to get your part. If you have to iteratively talk to the machinist about what it is you want, they're not going to like that because it takes their time away from what they wanted to be doing. And their favorite thing to do, if they don't like you, or if they think you're a young punk, right? Do we still use that word? You guys know what I mean, right? If they think you're a young punk engineer that thinks they know everything, they will make you exactly what you asked for, especially when they know it won't work. And the complexity of your parts and the fixturing required to hold them is going to impact the time it takes, whether or not the tooling's on hand, and don't forget the quality of your design. You got to know what you're making. So it's okay to go talk to the cranky old machinist and say, I think I want to make something that looks sort of like this, that does sort of like this. It's okay to have that conversation with them. Don't make them a drawing and say, make this. If you only sort of think you know what it is you want, go talk to them, have the conversation. You have sketches, drawings, solid models, and have you specified tolerances, dimensions, right? We talked about all this. So if you don't give them enough information, they can't make the part you want. If you give them conflicting information, they will decide which piece to use, especially if they know it will make your part not work. Unless they like you, in which case they will choose the piece of information to use that will make your part work while you're making it this way. So this specifically applies to design groups. If you're the person talking to the machinist, be the person that knows why you decided to put this feature in this spot, why this hole has a chamfer, why this is a threaded hole and this is a clearance hole. If you don't know those answers, if the machinist is trying to help you save time and money, and you don't know the answers to their question, you should bring somebody who does. This is engineering. Choice one. If you can buy the part, you really better be able to explain why you want to make it instead. Because especially if it's a commodity style part, right? So if it's a screw that you could buy at the hardware store, there is a very small chance that you'll be able to make it cheaper than the people who make it and sell it to the hardware store. So can it be assembled out of off-the-shelf components? Yes, almost always cheaper. All right, so what should you make it out of? So this also comes up with especially prototype work at places like WPI. So if you're working in a professor's lab and they say, here, take this piece of metal and bring it to the shop and make these pieces of chalk, right? So this rectangular piece of stuff isn't the ideal material to make little round pieces out of, but they would fit inside it. So it doesn't violate laws of physics. It's physically possible to turn this into little round things, but it's unlikely. So if you're modifying an existing part, then what's it cost to replace the part if we screw up? So you say, oh, I got this thing that came off our machine and we just need to drill this hole in it. Well, what if I split the thing in two when I drill the hole? What's the cost to replace the thing that you have? So consider those things. Do you have, don't just assume that the scrap material you have laying around is the right material. And this is especially for WPI students. Don't go out and buy the material until you've talked to somebody that's going to help you make the part. And again, it's because you could buy a volume of material that all of your parts fit inside, but it's better off buying little pieces that they don't have to nest inside. So, all right, what should you make it out of? And the design part of the process is your job as the engineers. Don't forget that. That doesn't mean you can't go ask the machinist for help. And certainly you should go ask if you have access to the manufacturing people and you have an idea when it's at the sketch stage. If you get a chance, just say, hey, I want to make something that looks sort of like this. Can you give me any advice? If you do that, then those people are going to want to help you learn how to design things that can be more easily manufactured. If you have the chance, if you're interacting on the shop floor, some of you will probably be in charge of a machine shop at some point in the next 5 years. So your job will be to manage the operations of that machine shop. I don't know which ones of you, but I bet you it will happen. And you need to learn as much about the setup, the fixturing, and all those things, those tricks that those real machinists know. And you need to document that so that you can help your company fill that skills gap, because we're not going to hire new machinists because there aren't going to be any. So therefore, your job is going to be able to design things that don't require the skill of a machinist to make. Design part is your process. Yeah, okay, it takes longer. Didn't we do this already? Oh yeah, don't say things I need this ASAP. ASAP means two different things to me. One, it means I don't do anything else until you have the thing in your hand, right? That's the one you'd like it to mean, right? It also means, oh, when I get around to it, I'll make it. It means those two things to me, and I put even weight between them. I realize you don't, but if I'm the cranky old machinist that day, so yeah, this is at WPI, so I have to do my experiment today, so I need all the parts. Should have thought about that in advance. I've got my SolidWorks done. When can I pick up my parts? So here at the WPI Manufacturing Labs, we don't operate a job shop. If you want to drop off your SolidWorks and pick up your parts, you need to use a job shop. Here we will empower you to make your own parts, but you guys know that you're in M1800. I have to show this to my advisor today. Yeah, that's not the day to show up and ask for help. And I just need this one simple thing. I've heard that many times. It usually takes about 3 hours. All right, so tomorrow we're going to talk about group project. We're going to talk about the CAM project, and we're going to talk about economics in manufacturing.